Hello everyone. In today's session, I am going to discuss the third part of digital electronics, which is data representation. In the last two classes, I have covered what is number systems and what are its conversation. And in the second lecture, I covered what are the basic operations like binary addition, binary subtraction, binary multiplication and binary division. In the lecture number 3, that means in this lecture I am going to cover the very useful and important topic, which is data representation. So here the name itself says the way in which we are representing the data in digital. So in digital, how we are gonna represent the data is nothing but data representation. So in digital, the data can be represented in two ways. The first way is unsigned data representation. Unsigned data representation, and the second way we have is signed data representation. Signed data representation. In these two ways we are going to represent the data, and coming to here, it is having unsigned magnitude form. Again another classification, unsigned magnitude form. Here coming to signed data representation, we have three types. The first type we have signed magnitude form. Signed magnitude form. Okay, and the second type we have ones complement form. And next one we have twos complement form. Okay, these three types we are going to represent the data in signed magnitude form. And coming to unsigned format, we have only one type, which is unsigned magnitude form. So now let us discuss which format is useful for us and how to represent the data in various format. Instead of having unsigned magnitude form or unsigned format, why we are going for the signed form? Everything here we are going to discuss, right? So now let me write unsigned form. Okay, unsigned form. So in the unsigned form, what is the first type? Directly I am writing unsigned magnitude form. Okay, the name itself says here unsigned means no sign. For example, if I write 6, if this 6 is having no sign, means defaultly the number is considered as plus 6, right? No sign means it is a positive number. Okay, here by using unsigned magnitude form, we can able to represent only positive numbers. The drawback is we can't represent no negative numbers. We can't able to represent negative numbers. This is the drawback. So why do we require these negative numbers? You can take some practical example, like let us take in industry, let us take a robot. Okay, we will use robot which will move forward and backward and monitor in industries. So let us take a robot. For example, in industry this robot want to move forward direction. Okay, so let us suppose it will use positive numbers. In digital, The same robot wants to move backward direction, okay, backward direction, then we compulsory required negative numbers. As you can see, in the unsigned magnitude format, we have only positive numbers. There were no negative numbers. So this is the drawback. So robot can always able to move forward. The same robot can't able to come back. To come back, we need to use the negative numbers, okay, which is not possible in the unsigned magnitude form. So hence the drawback here is no negative numbers. To have negative numbers, we are moving to the format signed form, okay. So kindly note down this, the various formats that I given, kindly note down these formats. Now let us discuss the next format, which is signed form. In the signed form, we have three types: signed magnitude and 1's complement, 2's complement. So in the signed form, I am going to discuss signed magnitude form, okay. Here MSB represent sign, means 0 for positive, 1 for negative, and remaining bits represents magnitude, okay. For example, I want to represent a number plus 0. Plus means sign, positive means I need to write with a 0. So MSB always points sign, that is what I said. And remaining bit 0, remaining bits will point magnitude. 0, let us suppose in 3-bit format I am writing. How to represent 0? 0 can be represented as 0, 0, 0. So plus 0 value here is 0, 0, 0, 0. Suppose I want to represent minus 0 in signed magnitude form. So how to represent minus 0 in signed magnitude form? Minus means 1. So I clearly told that MSB always gives sign. So sign is negative. Negative means here for negative 1 we need to write. So the rest bits 0 in 3-bit form, it is 0, 0, 0. Okay. So here we can able to represent, the advantage of signed magnitude format is we can able to represent the both positive numbers and negative numbers. But what is the drawback? Why we are going for the next formats like 1's complement and 2's complement? So here the drawback is unique representation is not possible. Unique representation, what is meant by unique representation? Let us see here, is not possible. Means, what does it mean is, so if you consider plus 0 and minus 0, so this is 0, 0 plus means very nearer, 0 minus means very nearer, right? 0 plus and 0 minus, anyhow it is 0, it is giving the same information, okay? Even though 0 is giving the same information, very nearer values, we are using different representation. We are using different type of representation. We are not using the same type of representation. So for the same kind of work, like I need to go to one place. So for the same kind of work we are using two vehicles. So here we are wasting hardware, right? So always in digital we need to save the hardware, okay? We need to save the cost. We need to increase its speed. We need to reduce its propagation delay time. Coming to here, plus 0, minus 0 are doing same thing, okay? Even though they are doing same thing, we need to have different logic here, means hardware is going to increase. Plus 0 means we need to use one type of logic because 0 0 0 0. Minus 0 means we need to use the another type of logic, means 0 anyhow, plus 0 or minus 0 it is going to be 0. Okay, it is taking two different types of representation. That means our hardware is going to increase. That is the drawback. That's why I told you that very clearly. Unique representation is not possible in the signed magnitude form. So it is taking different types of representation. With example I shown how it is taking different types of representation. So we taken plus 0. Plus 0 for it is using 0 0 0 0. Next I taken minus 0. Minus 0 for it is taking 1 0 0 0. Means plus 0 minus 0 is giving same information. The hardware is increased because there is no unique representation, there is a different types of representation. To overcome this type of problem, to avoid this, we are going to use 2's complement. So this 2's complement is generally obtained by adding 1 to the 1's complement. So adding 1 to the 1's complement, we are going to obtain the 2's complement. The advantage of 2's complement is unique representation is possible. Plus 0 and minus 0 both are taking only same types of representation. That I am going to show you with one example. So first let me discuss anyhow 2's complement that we are going to obtain it by adding 1 to 1's complement. So first let me discuss what is 1's complement, okay, and what is 2's complement, what are its rules. So first let me clearly discuss this, then after discussion of this I will go with some example. Okay, so the first rule here is zeros are converted into ones and ones are converted into zeros. 1's complement is whenever you get 0, replace as 1, whenever you obtained 1, write it as 0. And second thing, 1's complement of 1's complement is itself same number. For example, so let me erase here, let me first complete 1's complement. For example, 1 0 1 0, what is its 1's complement? I told you clearly, whenever 0 is there write 1, whenever 1 is there write 0. That means, so 0 1 0 1, this is the first time 1's complement. I told you that 1's complement of 1's complement is itself. So once again you do 1's complement, what you will get? 0 can be written as 1, 1 can be written as 0, 0 can be written as 1, 1 can be written as 0. So 1's complement of 1's complement, you will get itself, means same number, yes or no? Hence I written itself. This is the second rule in the 1's complement. And coming to the third rule in 1's complement, while doing addition, okay, while performing addition, if we get any carry, let us suppose 1 0 1 1, so you can add these two, okay, you can add these two, 0 plus 1 is 1, 1 plus 1 is 1 0. The carry should be added to the next LSB, next position LSB. That means carry should be added here. So 1 plus 1 is 1 0, 0 plus 1 is 1. So the answer is 1 0. So remember this. So while performing the addition, these three rules are important. Rule number 1 is zeros are converted into ones and ones are converted into zeros. Rule number 2 is 1's complement of 1's complement is itself. Rule number 3 is while performing the addition, if we get any carry, carry will be forwarded to the next LSB and it will going to be added. Okay, write down these 3 rules. All of you note down these 3 rules. These are very important. All of you note down these 3 rules. So 1's complement of 1's complement is itself. Zeros are converted into 1's and 1's are converted into zeros. While doing the addition, carry will be forwarded to the next position. Okay, complements are used for only negative numbers. So complements are used for only negative numbers. Complements are not meant for positive numbers. So what is the drawback? The same drawback. Unique representation is not possible here. So same drawback, whatever the drawback you got in signed magnitude form will be continued in 1's complement form. What is the drawback? These two are equal. So the drawback is no unique representation. So let us observe here why it's going to be plus 0 minus 0. I told you very clearly, for positive numbers we are not going to do complement. For negative numbers only we need to perform the complement. Plus means what? 0. 0 in 3-bit format, let us suppose 3-bit. So this is sign. So remaining bit 0 0 0, because for positive numbers we are not going to perform any complement. So coming to this, minus means 1 sign. 0 in 3-bit form is 0 0 0, but as it is a negative number, for negative number we need to perform complement. So here the complement we are studying is 1's, so we are performing 1's complement. First 0 can be written as 0 0 0. Its 1's complement is 1 1 1. Hence the answer is 1 1 1. Okay, now what is the logic here? What is the drawback here? So logic is 1's complement. Then what is the drawback here? The drawback is plus 0 is taking one type of representation. Minus 0 is taking another type of representation. The same drawback follows. Different types of representation is going to happen here. There is no unique representation is the drawback. To overcome this, that's why I told you we are going to study the 2's complement. So what is 2's complement? You can observe here carefully. So in 2's complement, let me give you 3 rules. The first rule is 2's complement can be obtained by adding 1 to the 1's complement. Okay, as I said, 1's complement plus 1 gives 2's complement. And the second rule we have 2's complement of 2's complement is itself same number. I'll show you with one example. Okay, so 1 0 1 0. Perform its 2's complement first. So there are 2 methods to do 2's complement. So let me take you another slide. 1 0 1 0. First method I will do 1's complement, then I'll add 1. So what is its 1's complement? 0 1 0 1. Then I will add 1. 1 1 1 0. Okay, this is the 2's complement. Again do its 2's complement. First do 1's complement. 1 0 0 1. Add 1 1 0 1 0 1. So 2's complement of 2's complement is itself. Okay, 2 times I done 2's complement. In order to do the 2's complement, first I will done 1's complement, later I added 1. 1's complement plus 1 is equal to 2's complement. Okay, then now I am going to use the shortcut here. All of you observe the shortcut here. without having this many number of steps. How to perform 2's complement? First, write down the number 1010. Okay. Now start from LSB. All of you start from LSB. What is the value in LSB? The value in LSB is 0. Write it as it is. Next, write down the next bit. Until 1 comes, write it. After 1 written, whatever the bits remaining, complement it. Just do 1's complement. Invert it. 0, 1. This is your direct 2's complement. If you want, you can check here. Have you got the same or not? Instead of doing 1's complement and adding 1. Once again, I will explain. So again, we are performing 2's complement. As I said, you start from LSB. If LSB is 0, write as it is, move to the next position. If LSB is 1, write 1 once. Whatever the lefted next position bits, whatever the lefted bits, for the lefted bits you need to perform complement. This is the small logic here. Okay. So first I am writing LSB. LSB is 0, hence I am writing as it is. If it is 0, don't worry, move to the next position. 0 is not going to affect anything. If it is 1, write that 1 once. After writing that 1 once, whatever the lefted bits, perform complement. So simply 1 0. So 2's complement of 2's complement is itself or not? Same number or not? Once again, I'll explain you the shortcut with 2 more examples. Here, let me take some big numbers 0 1 0 1 0. These are 2 examples. Let me perform you the 2's complement. So what I said, start from LSB. So this is what? My LSB, least significant bit. So what is my LSB? 1. So that 1, write it once. One time you need to write. After writing 1 once, for lefted bits, whatever the bits are lefted, for that bits you need to invert or complement. So 1's complement. 0 1 0 1 0. This is your direct 2's complement. No need to perform 1's complement again, adding 1, getting confusion in addition. Don't confuse anything. They directly apply this shortcut method. In the same manner, so start from LSB. If 0 comes, move to the next position. Okay, what is the next position? 1. Until 1 comes, write that 1 once. After that, the lefted position, you need to perform the complement. So this is your direct 2's complement. Okay, note down this all. All of you note down this. Everyone, whoever watching this lecture, kindly note down this. Okay, now what we have to do? Here I said 2's complement of 2's complement is itself, and third point I gonna explain, while performing addition, while doing addition, if we get carry, okay, so 1 0 1 1, so we are doing addition by using 2's complement. So 0 plus 1 is 1, 1 plus 1 is 1 0. The carry will be ignored, neglected. In 1's complement, carry is forwarded, right? Coming to here, the carry will be, if we get carry, carry will be neglected or ignored. So this is the rule here. Now we will see the advantage of 2's complement. I told you very clear, we are going to save the hardware by using 2's complement. That is, unique representation is possible in 2's complement. So how it is possible? The advantage is unique representation is possible in 2's complement system. So how it is possible? Let's observe here. Plus 0. Anyhow, I told you very clearly that for positive numbers we are not going to perform any complement. So plus means what? Sign. Sign is MSB. Plus for 0. 0 in 3 bit, again I consider. 0 in 3 bit, as it is a positive number, no need to do any complement, hence it is 0 0 0. So next minus 0. First minus means what? 1. 0 in 3 bit is 0 0 0. So I need to perform 2's complement. 2's complement can be obtained by adding 1 to 1's complement. 1's complement plus 1. First for 3 zeros, I will perform 1's complement. 1 1 1. So 1 1 1. This is 1's complement. Now we want 2's complement. We need to add plus 1. So 1 plus 1 is 1 0, 1 plus 1 is 1 0, 1 plus 1 is 1 0, 1 plus 1 is 1 0. Sum is 0, carry is 1. So I clearly told you that in 2's complement the carry will be ignored or neglected. Now you can see plus 0 means 4 zeros and minus 0 means also 4 zeros. 4 zeros, 4 zeros. That means unique representation is possible. The same way of representation we are doing by using the which complement? 2's complement. That means we are saving the hardware here. Okay, no need to have some extra hardware. So note down this. Now I will tell you the ranges of various formats. Note down this. So let's discuss the ranges of various formats. So first range is unsigned magnitude form. As you can know that there are no negative numbers, so numbers are starts from 0. 0 to, for n bit we know 2 to the power of n levels are possible. So to get the maximum count, always we need to subtract 1, because for 3 bit the representation will be 000 to 111, means up to 7. 7 is the highest number. So 2 to the power of n minus 1. These are positive numbers. This is the range in unsigned magnitude form. For n bit, 2 to the power of n levels are possible. To get the highest value, we need to subtract 1. Okay, note down this unsigned magnitude form. Now let's see the next form, which is signed magnitude form and 1's complement. Both have the same drawback. Hence both ranges are same. So here both negative numbers and positive numbers are possible. So for n bit, generally 2 to the power of n levels are possible. Okay, but here both negative and positive, plus and minus, 2 numbers are possible. Hence I am sharing half of the numbers are for negative, 2 to the power of n minus 1. 2 to the power of n by 2. Half of the numbers are positive. To get the maximum count, what I will do? Always subtract 1. Always subtract 1. So what is the range now? Minus 2 to the power of n minus 1 minus 1 2 plus 2 to the power of n minus 1. If 2 comes above, bases are equal, power should be added by using that concept, minus 1. So this is the range of, very important, for both signed magnitude form and 1's complement form. Note down these two formats. Okay, so coming to 2's complement format, we can able to save one negative 0, right? Minus 0. Hence, without this we need to write. So 2's complement format, so minus 2 to the power of n minus 1 2 plus 2 to the power of n minus 1 minus 1. We can able to save one negative 0. Plus 0 and minus 0 are giving the same unique representation. So this is the range for 2's complement format. 2's complement format. Okay. So in this way there are various types of representations like unsigned magnitude form, signed magnitude form, and 1's complement form and 2's complement. Here I am continuing the next topic, which is 9's and 10's complements, which is also important, and 15's and 16's, which is f's and f plus 1's complement. So let me discuss this. For example, if someone asks you to do 9's and 10's complement of 443, 543, 3 different digits, single digit, 2 digit, 3 digit I am giving, then what you need to do is write down 9, that many 9's above, and subtract. So answer is 6, 9 minus 3 is 6, 5, 4. Here 6, 5, here 5. So this is your 9's complement. So add 1 to the 9's complement. By adding 1 to the 9's complement, you are going to get 10's complement, which is 7, 5, 4. Okay, 7, 5, again 6. Okay, by adding 1 to the 9's complement, you are going to get 10's complement. And note down this example. So with the formula, if you want, I'll give you the formula. R power n minus 1 minus n is your 9's complement. R power n minus 1 minus n plus 1 will give your 10's complement. So what is this R? R is radix or base. R is radix or base. N is number of digits. Capital N is given number. Now you can have one example here. So same thing 43 we will take. Okay, what is the radix? Generally it is a decimal, right? So radix is 10. Number of digits are how many? In 43, 2 digits are there. 10 square minus 1. 10 square minus 1 is 900 minus 1. 99. Okay, 99. Minus given number. What is the given number? 43. That is what we done. By adding 1 to that, we got 10's complement. Okay, this is formula based. If any time it will comes in exam about the formula, through formula based also we can able to solve this. Note down this, all of you. And finally we will have 15's and 16's complement. Okay, this is also very simple. So for example, I want 15's complement of BA. So 16's complement can be written as f plus 1's complement, which will be obtained by adding 15's complement plus 1, which is f's complement plus 1. So 15's complement, how to do this? Write down that many number of 15's. 15 means f. 15 minus 10, how much? 5. 15 minus 11, 4. 15 minus 10, 5. 15 minus 11, 4. This is your 15's complement. Just add 1, 6, 4, 5, 4. This is your 16's or f plus 1's complement. So in this way we can able to do this complement. So in this lecture I clearly given as the part of third lecture in digital electronics. If you missed the previous two lectures, please go through the last two lectures. In lecture 1, I explained what is number system and what are the number system conversions. Lecture 2, I explained what are the basic operations like binary addition, subtraction, multiplication and division. Lecture 3, I explained about how to represent the data, that is data representation in digital. In that unsigned, signed, 1's complement, 2's complement and 9's complement, 10's complement, 15's complement, 16's complement. So this type of theory, concept, synopsis, everything I covered here. Okay, so keep following two things. The first thing, our YouTube channel, which is Technogate space education. So you are going to get series of some free video lectures here. Okay, so Technogate space education, and also this is YouTube channel name, YouTube channel. Kindly everyone subscribe and like, share, comment on the video. However you feel this video lecture, it is going to some boosting for us to do some new lectures also, right? So everyone please like, share and comment on this kind of lectures. And then after, you please follow me on Instagram also. My Instagram ID is Technogate_education. So you kindly follow me on this Instagram, Technogate_education. Further, if you have any doubts in this lecture, after listening this lecture, if you have any doubts, please type me your question to my WhatsApp number. Okay, if you are getting any doubts, you please type your query to my WhatsApp number. I'll be responding to you 9391202202. So in the entire lectures of digital electronics, I am going to give you the best content. So all of you follow the series. Don't directly listen the middle section. So first you listen the first part. After completion of first part, then go through the second part. Okay, after second part, if you missed any previous two parts, just WhatsApp me. I am going to give the two links. Then come to the third part, complete the third part. We'll see the next part of digital electronics very soon. Thank you.